Ladies and gentlemen, welcome back to your cybersecurity series. My name is Vlad and I'm here to help you and support you in your cybersecurity journey, even if perhaps you don't have a technical background. Today it's episode 26 and we are continuing our journey on cryptography. And this is it. This is really the point where we are reaching modern cryptography. We will talk about all the techniques or everything that is more or less embedded within your devices, so your mobile phone, your laptops, some of the software that you might be using on a daily basis, even perhaps without knowing it. But before we get to that, we need to set the scene and give you the basics, the principles. And today we will focus on the XOR operations, so exclusive or written XOR, but more on that in a couple of minutes. As I said in the introduction, I am really done with the historical approach on cryptography. We talked about what the Romans, the Greeks were using in terms of techniques, and that's really useful to give you the main elements of language, the main elements of understanding. We talked about the principles, for example, what Kirchhoff stated a couple of centuries ago, saying that the secrecy has to be on the cryptographic key, and that's really central, that's fundamental. And you need to understand that the secrecy is not on the algorithm or on the device. I gave you the perfect example of the Enigma machine that was being used by the Germans in the Second World War. And essentially, even if the Allies managed to pull apart this machine and understand everything, the secrecy was really on the configuration of the starting positions of the different rotors. But again, we will still leverage on all of those notions starting with modern cryptography today. So, modern cryptography, everything really relies on the processing unit. So, the CPU or the processor, it's the component that you see here. It's in a shape of square. Basically, it's easily recognizable, even if you are not an engineer. It's more or less in the middle of the motherboard of any device. And the idea is that it's really the brain of your device. It's really the components that will perform all the operations, all the calculations to make sure that you are running your software, your operating system smoothly. But even if from a human perspective, we are managing contextual windows, we are playing with text, we are playing with pictures or media content in general, from a CPU perspective, so from a processor perspective, it only manages zeros and ones. And to do complex operations with that, you need to have a certain algebra, so a certain number of operations that you can perform. You can do additions, subtractions, multiplications, and so on. And there is what we call Boolean algebra. So again, managing zeros and ones. One way to illustrate that, and I found this picture of Halloween logical gates masks. The idea is that we are going to depict two disks. So a first disk on the left that we will call trick, and the second disk on the right that we are calling treat. And of course, when you do trick or treat, the result is correct. So the result is true. That's what we say. So zeros and ones, it's equivalent to true or false, or true being the one and false being the zero. And the idea is that here in this small comics, the area that is highlighted in orange equals true or equals one. So when we say trick or treat, the area that is correct or that is true is basically the combination of both disks. If you say trick and treat, you are only referring to the intersection of both disks. And finally, the notion that is of interest today, when we say trick XOR treat, this time we are actually referring to the part of each disk that is not common, that is not shared across the two disks. So it's really an exclusion operator, and it's really useful in modern cryptography. Of course, if you dive more on your own around Boolean algebra, you will come across more advanced or more complex notions. For example, you might come across the NOR, so not or operator. It really refers to everything that is not trick or treat. And as you can see, this time the orange section is everything except the two disks that are left in white. Similarly, you also have an operator that corresponds to not and called NAND that corresponds to everything that is not the intersection. And there is also an XOR, but I will not dive on that. It's basically the same thing, everything that is not XOR. One way to represent that, to make sure that you have also a better understanding of how do we use it when we talk about zeros and ones, it's to do basically a logic gate. So we are going to take two inputs, A and B, and depending on the possible combinations of A and B, we are going to compute A XOR B. So the XOR, as you can see, it's always represented by a plus sign that is within a dark circle. So basically, when we do 0 XOR 0, that is also equal to 0. 1 XOR 1 is also equal to 0. Because if you may remember, we are really interested in the areas of the disks that are distinct, meaning that it really corresponds to the operation of A and B must be different. So when A is 0 and B is 1, A XOR B is true, so equals 1. When A is 1 and B is 0, same thing, A XOR B equals 1, meaning that it's true. So it's really here also to illustrate the joke that I made in the beginning. So I know it's a bit of a boomer joke, but why did the two bits break up after using XOR? The answer is because one of them always had to be different. So that's really the idea. A XOR B equals 1 when A and B are different. So is it the perfect cipher, and really what is the link with modern cryptography? The idea is that we are going to use XOR as an operator to encrypt or decrypt messages. So first thing first, the encryption. How does it work? Basically, we have a plain text message. Our message is going to be composed of course, several bits of information. And the idea is that we are going to make a XOR operation with an encryption key. So the encryption key will also be composed of a series of bits. So here I have taken just the logical gate. So as you can see, 0 XOR 0 equals 0, etc. And the product of the XOR operation is going to be our ciphertext. Okay, so far so good. I hope it is for you. Don't hesitate to put a comment if something is unclear. The idea is that we can push the reasoning a bit further. We are going to look at what's happening when we do the ciphertext, so C, and we are going to XOR that again with the encryption key. So this is equivalent to doing our plaintext message, XOR the key again. And also one notion that is interesting is that the XOR, I mean, it doesn't matter if you do A XOR B or B XOR A, it's absolutely the same thing. So here, when we have the ciphertext that is 0 and we are doing a XOR with the encryption key, 0 XOR 0 is again 0. We do it the same, 1 and 1, we have a 0, 0 and 1 is different, so we get a 1, 1 and 0, again, our encryption key and ciphertext are different, so we get a 1. And what we can look at is that in the end, when we do our ciphertext XOR the encryption key, we get back our plaintext message. And that is a fantastic property of the XOR operation. When you do XOR twice in a row with the same element, so here the encryption key, you get back the original message. And that's absolutely fantastic for modern computers because, first of all, as we say, the XOR operation is part of the built-in mechanisms of modern processors. So it's something that the processors can compute extremely fast and it's symmetric. So we are using the same key for encryption and decryption. It's not really, let's say, an advantage. I mean, it has certain advantages because it's straightforward. Of course, then everything relies on this key. We will call that a secret key because, of course, if you lose the key or if you leak some information about the key, the confidentiality of your correspondence could, of course, be compromised. I will illustrate that with a modern message composed of letters. Maybe it's easier for you to apprehend than zeros and ones. So here, let's say we have a short message. Our message is just 3 characters. We want to send an SOS. What we are going to do is transpose the SOS characters into ASCII zeros and ones. And basically, ASCII, it's a set of table. So here it's not really zeros and ones. I'm showing that in X value, so hexadecimal. But the idea, as you can see in the table, is that any character can be depicted by hexadecimal values. When we transform that back into bits, we get one character can be encoded with 8 bits. So for example, the character S will be encoded in or encoded by 01010011. Character O will be encoded by 01001111. What we are going to do is choose an encryption key. So our encryption key that we call K here, we need to find or to choose three characters that will be, of course, secret in order to encrypt our message. Here, I chose the three characters PIN because we always talk about the PIN code, but basically, you could decide on any characters. You could say AAA, B, C, G, whatever you want. So here, same thing. We take our three characters from the key and we are transforming them into a series of bytes, a series of bits. Sorry, my bad, and we are going to XOR them. So we are going to XOR bit by bit our message with the key. So if you do that, you will get the ciphertext. So if we go on the first character of the message is 0, first character of the key is also a 0, so 0 XOR 0 equals 0. If you look at the very far right, we have the last character, that is the last character of the letter S. This is a 1, and the last character of the letter N, this is a 0. So 1 XOR 0 equals 1. So what you get at the end is not really three characters, because if you go back to the ASCII table, as you can see here, sometimes depending on the values we can get numbers, we can get letters in capitalized, we can get lowercase letters, and we can sometimes also get weird characters. So for example, as you can see here in position 03, you get ETX. So ETX is actually not a character, it's something that represents the end of text. So it is something that is not shown to the user, but it's really used by the processor and by the software to know when exactly is a sentence finalized or when is a word finalized. So some of those elements, they are not displayed to the user, but they still exist within the ASCII matrix, which, as you can imagine, makes it even more complex to decipher. So in the end, our ciphertext is a set of three characters which will not be printed on a screen, but if you look at the bitcode, you will get end of text, acknowledge, and group separator. So in the end, if we do a short recap on that, is XOR the perfect cipher? Is it the perfect method? It has two great advantages. First one, it's fast. Second one, it's straightforward because it's a symmetric encryption. However, there are a few limitations. First of all, it only meets the confidentiality requirements. If you go back to my, I think, first or second video, we talked about the three properties of cybersecurity: confidentiality, integrity, and availability. Here, doing the XOR does not give you any information on whether or not the message has been modified. So the XOR operation alone is a great asset, but only to preserve the confidentiality. And it's only applicable for one-time paths, meaning only once you can apply your secret key. If you apply the same secret key on several messages, in the end, if they are intercepted, so if the cipher version of those messages is intercepted, by XORing them and doing it on multiple occasions, you could manage to find back the encryption key. This is something that has been done on modern encryption algorithms. I told you, I think, in the previous video of the web, which is a Wi-Fi authentication protocol. The web protocol was vulnerable to that type of messages because, in the end, the encryption keys that were being used, some of the encryption keys were being reused. That's the point. And basically, there was a counter that was reset and going back at 0. And every time that they were reusing the same message, in the end, they were leaking some information on the encryption key, allowing unauthorized users to log in onto the Wi-Fi. So it's the same principle with the XOR operation. It's extremely strong, almost unbreakable. However, you need to use it only once. And finally, the most striking limitations is that the key, as you have seen in my previous example, the key here has to be exactly the same length as our message. So the algorithm is strong itself. However, the use that we need to have, it's a bit complex because we need a key that is the same length. If you picture, for example, let's say your disk, your hard drive, imagine you want to encrypt your hard drive for confidentiality. You would need a second hard drive that would be the encryption key to encrypt the first one. So it's not really something practical. It's not something that we can scale up. So even though the XOR operation shows great promises, it's not applicable on its own, which is why in the next video we'll talk about block ciphers, and how we are circumventing a bit these difficulties or those limitations from the XOR cipher. So I hope you enjoyed this introduction video. Again, we will build on that, so don't forget everything about the XOR. I told you it's extremely central within modern cryptography, and see you soon in the next video. Take care.